Now we are going to discuss the topics of vacuum consolidation and blast densification. So let's start from the vacuum consolidation. Vacuum consolidation was first proposed in the early 1950s by Gell-Mann in 1952, the developer of the prefabricated vertical wake train. In the 1960s, isolated studies of the vacuum-induced or assisted consolidation continued for the next 2 decades. However, except for the specialized application like landslide stabilization, vacuum consolidation was not seriously investigated as an alternate to convenient surcharging until recently due to the low cost of placing and removing surcharge fills and difficulties involving in applying and maintaining the vacuum. The steadily increasing direct and indirect costs of placing and removing surcharge fill and the advent of technology for sealing landfills with impervious membranes for landfill gas extraction systems have now made vacuum consolidation an economically viable method as a replacement for or supplement to surcharge fill. Vacuum consolidation is an effective means for accelerating the improvement of the saturated soft soils. The soil site is covered with an airtight membrane and a vacuum is created underneath by using a dual venturi and vacuum pump. So this point is very important. The soil site is covered with an airtight membrane and a vacuum is created underneath by using a dual venturi and vacuum pump. The technology can provide an equivalent preloading of about 4.5 meter high as compared with a conventional surcharging fill. Instead of increasing the effective stress in the soil mass by increasing the total stress as in the conventional mechanical surcharging, vacuum-assisted consolidation preloads the soil by reducing the pore pressure while maintaining a constant total stress. The effectiveness can be increased when applied with combination of surcharge fill. Field experience indicates a substantial cost and time savings by this technology compared to the conventional surcharging. So here you can see the Menard vacuum consolidation. So you can see that we are having the vertical drains which have been linked with the horizontal drain, and that setup, that arrangement has been linked to the pump, and by inducing the vacuum we can speed up the drainage process. So in this way, settlement will take place quickly. The current main application of vacuum-assisted consolidation include replacement of standard preload techniques, eliminating the risk of preloading induced foundation failures, combining vacuum consolidation with preloading in scare fill areas, that means the dangerous areas, weak areas. The method has been used to build large development projects on thick compressible soil. Combining vacuum consolidation with surcharge preloading to increase foundation stability and thereby optimize preloading stage sequence and reduce project time. Equipment and the construction process. So this slide is very important. The vacuum consolidation construction process involves the following steps. Number one, placing a free drainage sand blanket 60 to 80 cm thickness above the saturated ground in order to provide for a working platform. Installation of vertical drain generally of 5 cm in equivalent diameter. Installation of closely spaced horizontal drains at the base of the sand blanket using a special laser technique to maintain them horizontal. Next step, the horizontal drains in the longitudinal and transverse directions are linked through connections. Excavation of trenches around the perimeter of the preload area to a depth of about 50 cm below the groundwater level and filled with an impervious bentonite polyacrylate slurry for subsequent sealing of the impermeable membrane along the perimeter. The transverse connectors are linked to the edge of the peripheral trench. They are then connected to the prefabricated module designed to withstand future pressure due to vacuum. Installation of the impermeable membrane on the ground surface and sealing it along the peripheral trenches. The membrane is delivered to the site folded and rolled in elements of approximately 1000 square meter. The membrane elements are welded together or joined. Here the word welding is being used for the joining. The membrane elements are welded together and laid in the peripheral trench where they are sealed with the bentonite polyacrylate slurry. The trenches are backfilled and filled with water to improve the tight sealing between the membrane and the bentonite aquakeep slurry. Next step, vacuum pumps are connected to the prefabricated discharge module extending from the trenches. The vacuum station consists of specifically designed high-efficiency vacuum pumps acting solely on the gas phase in conjunction with the conventional vacuum pumps allowing liquid and gas suction. The process combines dewatering and vacuum action to maintain the water table at the base of the granular platform during the entire application of the consolidation process. Eventually, an additional drainage system is installed at the required depth to allow for a conventional dewatering under the membrane. Indeed, the fill will maintain a non-submerged action even when it has settled below the original groundwater level. Therefore, with this technology, unlike the case of surcharge preloading, the load intensity will not decrease during the vacuum application. The discharge drains are manufactured by extrusion of cylindrical and perforated PVC. PVC means polyvinyl chloride. Use of suitable filter cloth with proper filtering properties to cover the perforated PVC avoids infiltration of sand and fines during vacuum application. The discharge drains are brought to the surface at every 150 meters spacing where they are connected by transverse drains to the vacuum station. Conceptual design. Vacuum-assisted consolidation provides an effective alternative to surcharging for preloading soils. Instead of increasing the effective stress in the soil mass by increasing the total stress using a conventional mechanical surcharging, vacuum-assisted consolidation preloads the soil by reducing the pore pressure while maintaining constant total stress. So total stress remains constant in this technique. In essence, geotechnical design analysis used to evaluate wick drain spacing and strength gain for preload spills are equally applicable to the engineering design of vacuum consolidation system. There are many technical and operational factors which play important roles in vacuum consolidation. Primary considerations Governing the effectiveness and economics of a selected VCP scheme include: VCP stands for Vacuum Assisted Consolidation Preloads. I will repeat, VCP stands for Vacuum Assisted Consolidation Preloads. Number 1, integrity of the membrane at the ground surface. Number 2, seal between the edges of the membrane and the ground. Number 3, soil stratification including permeable and seams within the clay deposit. And the fourth one is the depth to groundwater. Breaks in the membrane, a poor seal between the membrane and the ground, and weak drains extending into the layer of high hydraulic conductivity all tend to reduce vacuum efficiency. Success, so this point is very important. Success of a vacuum consolidation system depends upon a combination of technical know-how and careful implementation of design details. Now this slide is showing the two techniques which can be used in the vacuum consolidation. So you can see that in this case we are using the membrane at the top, and here there is no use of membrane. So this is, you can say, membrane system, and this is the membrane-less system. So in the vacuum consolidation we are having membrane system where the watertight membrane is being used, and here instead of using the membrane we are using the tubing system. And special cap drains are used, but the purpose is same. I mean to say the ultimate goal is same. With the help of vacuum or the suction we can speed up the process of drainage, and in this way you can get the desired consolidation settlement in a shorter period of time. Now you would find some case histories. First look at the advantages of vacuum assisted consolidation is well demonstrated by the pilot testing conducted in Ames, France for the construction of highway embankment on a very compressible saturated clay soil. As shown in the figure, you would see that the soil profile at this site indicates the presence of about 1.3 meter thick peat layer, highly organic soil, with a moisture content ranging from 400 to 900. Look at that. Underlain by about 2 meter thick, highly organic, compressible clay layer with moisture content ranging from 140 to 210%. The project plan called for the construction of a highway embankment 2.15 meter high across the site in order to protect the highway from floods. Alternative solutions including soil replacement, a raft foundation supported by piles, and conventional surcharge preloading were considered and rejected for economic reasons. For example, due to stability concerns, the conventional preload system required very gently sloping embankment with a base width of 65 meter, which was economically prohibitive. As vacuum consolidation has not been previously applied under such soil and moisture conditions, a pilot field testing program was implemented. The combined application of surcharging 1.3 meter and vacuum provided an equivalent preload of about 150 kPa after only 2 months of vacuum application, whereas under conventional surcharge, slope failure would have occurred at this site under a preloading stress of 35 kPa. Figure 4b depicts the monitored settlement record during the consolidation process. It indicates that the recorded settlement with vacuum consolidation is approximately equivalent to that induced by a 4.5 meter high surcharge embankment. Analysis of the settlement records indicated that at the end of the consolidation process, the settlement of the peat layer reached about 80% of the reference settlement that would have been induced by a 4.5 meter high surcharge embankment, while the settlement of the underlying highly organic clay reached about 50% of that of reference settlement. At the end of the vacuum application, the ground surface rebounded by about 3 cm during 48-hour period and then stabilized. During the vacuum application, the ground water level rose by about 40 cm up to the level of the horizontal drains, while the upper part of the granular fill remained dry. Following the pilot testing, the vacuum consolidation was selected as the best available solution for the consolidation of about 17,550 square meter along this highway construction site. So here you can see the figure. So look at the profile and look at that. First, simply the vertical drains were used. Then you can see the embankment has been placed upon that. So you are having this pattern of settlement. But when the vacuum consolidation is introduced, so you can see there is a remarkable increase in the settlement. The next case history, the A37 highway in the western part of France crosses 3 swamps. Swamp, that is, you can say, wet spongy land. The site is divided into 3 parts, each distant of 15 km. The first 2 swamp crossings are 500 meters long and the third one 70 meters long. The thickness of the highly compressible material reaches 12 meters. The final embankment height varies between 4 and 9 meters above grade. An initial study of the potential settlement had indicated that approximately 2 meters were to be expected for a 4-meter embankment height over a period of more than 50 years. Thus, preloading became necessary to accelerate the consolidation and to reduce the post-construction settlement to manageable magnitude. In view of the project size and the highly developed agriculture surrounding the proposed embankment, the transportation of additional fill for surcharge from a long distance, 50 miles, became economically prohibitive. The vacuum consolidation process was then thus selected as the only viable alternative to conventional surcharge. Figure 5 shows the settlement recorded during construction, first due to vertical drains only, then the substantial increase as vacuum is applied. VCP, that is, the vacuum assisted consolidation preloads, has permitted the construction of up to 6-meter high embankment within a 3-month period. Total settlement during this period was 1.7 meters, and the residual deformation anticipated for the next 30 years is estimated at 10 centimeter only. So this is the figure 5. You can see that you are having the pattern of settlement like this when there is only the vertical drains, and when the embankment is constructed you are having the improvement, and when the vacuum consolidation is introduced, so you can see there is remarkable improvement. Technology assessment. The efficiency of this technology has been demonstrated under different site conditions, where it has successfully provided cost-effective solutions to substantially accelerate the consolidation process while leading to significant saving in project cost. Unlike the case of conventional surcharge, VCP, VCP means vacuum assisted consolidation preloads, does not raise any stability concerns while resolving the environmental problems associated with the conventional method of surcharge preloading. The vacuum consolidation technique is often combined with surcharge preloading. The major practical advantage of the vacuum consolidation is that it generates in the granular layer an apparent cohesion due to the increase of active stress, and the granular layer provides a useful working platform to accelerate the surcharge backfilling process. Experience indicates that within days after a vacuum pump is turned on, construction vehicles can maneuver or move on the top of the membrane. Conclusions. Vacuum consolidation is an effective means for improvement of highly compressible soft soils. In essence, vacuum consolidation can yield an effective equivalent preload of about 4 to 5 meters of conventional surcharge fill. A combination of conventional surcharge with vacuum application can yield much higher equivalent preload. Experience from US and China and the case histories from France indicate that this technology can be applied cost effectively under various challenging site conditions. In certain difficult site conditions where the stability under the conventional surcharge is of concern, VCP, that is the vacuum assisted consolidation preloads, allows to cost effectively accelerate the consolidation process as compared to conventional stage loading. In Europe, the engineering use of vacuum consolidation is currently rapidly expanding, and it is of interest to note that this technology has been used to cost effectively replace conventional surcharge preloading for the development of about 57,000 square meter of industrial on-land application at the Channel Eurotunnel terminal. On-land applications are most suitable for soft soil sites with shallow groundwater level. Presence of stratified soils can render vacuum consolidation ineffective unless deeper vertical cutoff systems are installed. Recent field trials also indicate that on-land vacuum consolidation combined with dewatering can be an effective solution to further accelerate the consolidation process. Experience from on-land field application of this technology indicates a high potential for use of vacuum technology for improvement of existing hydraulic fills, strengthening weak sediments in the area floor adjacent to or beneath waterfront retaining facilities, and construction of fine-grained hydraulic fills during construction. Now we are going to discuss the blast densification. As you can get some idea from the word blast that here we are going to use some blasting technique for the densification of the soils. Blast densification is a ground improvement technique for densifying loose, relatively clean, cohesionless soils. So basically here we are having the concern with cohesionless soils. It increases the density of loose granular deposits above or below the water table. The explosive wave temporarily liquefy the soil, causing the soil particles to rearrange to a higher relative density as excess pore water pressure dissipate. It has been used to treat soils to depth of up to 40 meters. As depth increases, the size of the charge necessary to destroy the soil structure and liquefy the soil increases. Excess pore water pressure and settlement due to explosion are related to the ratio, this one, which is N sub h, that is known as the Hopkins number, where this W is the weight of the explosives equivalent kilogram of TNT. TNT stands for trinitrotoluene. I will repeat, trinitrotoluene. You can say this is an explosive substance used in blasting dynamite. And what is dynamite? Dynamite, you can say, a class of explosives made from nitroglycerin in an absorbent medium. R here, that is the radial distance from point of explosive in meter. If N sub h is less and in the range of 0.09 to 0.15, liquefaction does not occur and the equation can be used to estimate the safe distance from explosion. Now, through this example, you can see N sub h, that is 0.12, and the W is 10 kilogram. So the radial distance from the point of explosives, that is 17.95 meters. Experience with sandy soils in Netherlands suggested the following relationship obtained from statistical analysis of the field results. So these are the two relationships where N sub h is calculated using units of kilogram for W and meters for R. Berenson and Koch in 1983 state that for optimum densification, this ratio should be more than 0.8 is required. Blasting. Blasting is a technique that has been used successfully in many projects for the densification of granular soils. So we are focusing on the granular soils. The general soil grain sizes suitable for compaction by blasting are the same as those for compaction for vibroflotation. The process involves the detonation of explosive charges such as 60% dynamite at a certain depth below the ground surface in saturated soil. The lateral spacing of the charges varies from about 3 to 9 meters. 3 to 5 successive detonations are usually necessary to achieve the desired compaction. Compaction up to a relative density of about 80% up to a depth of about 18 meters over a large area can easily be achieved by using this process. Usually, explosive charges are placed at a depth of about 2/3 of the thickness of the soil layer desired to be compacted. The sphere of the influence of compaction by a 60% dynamite charge can be given as follows. So look at this simple formula. R, small r, is the sphere of influence. That means up to that radius you are having the influence of that explosion. W sub Ex, that is the weight of the explosive, that is the 60% dynamite. C is 0.0122 when Wex is in kilogram and R is in meter. Okay, weight of charge. There are some rough guidelines. W is equal to 164 multiplied by C multiplied by cube of R, where the W is the weight of explosive in Newton in this formula. C is the coefficient, that is 0.0025 for 60% detonator. R, that is the radius of influence. Arrangement of explosive, we are having the grid pattern, firing pattern from outside to inside. If you are having one particular site, we will start from the just outside and then will be coming to inside. Spacing 3 to 9 meter, less than 3 generally avoided. Depth of stratum to be densified 10 meter or less, and the depth of explosive is 2 by 3 of the depth. And this depth means the depth of the compressible material that you want to compact. And the compaction in one tire only. That means in one trial you will be able to compact. Depth of stratum to be densified when it is more than 10 meter, then the depth of charge greater than radius of sphere of influence. That's very important. And the compaction will be done in more than one trials, more than one tire. Materials and equipments: dynamite sticks, electric detonators, drilling equipment, backfill material, that is the sand, and the waterproof packets. So here you can see the dynamite sticks and electric detonator, you can see. Method: series of boreholes are drilled and pipe of 7.5 to 10 centimeter is driven to required depth. Dynamite sticks and detonators are wrapped in a waterproof bundle and is lowered through casing. Casing is withdrawn and a wad of paper or wood is placed against the charge of explosive to protect it from misfire. Boreholes are backfilled with sand to obtain full force of ballast. This is very, very important, that boreholes are to be backfilled with sand to obtain full force of ballast, because we want good packed sand to have the full force of blast. Electric circuit is closed to fire the charge. The charge is fired in definite pattern. For deeper deposit, blast is done in stages. Repeated shots are more effective than single larger one. Each successive blast in a given area will cause less densification than the one preceding. From you can say top 1 meter surface get disturbed and needs surface compaction. So here you can see different steps involved. This was the first step, this is the second, then this, and after blasting obviously the surface compaction is to be done. Now a few case studies. Highway 504 bridge over Coldwater Creek. The proposed location of bridge 12 over Coldwater Creek along State Route 504 was underlain by 40 meter of debris flow. Probably you are knowing the word debris. Debris means the scattered remains of something destroyed. I will repeat, debris means scattered remains of something destroyed. The debris flow. So when we say the debris flow means moving mass of losing, you can say the moving mass of loose soil with water and air. That is known as the debris flow. The debris flow was composed of very loose silty sand and gravel with boulder and cobbles. Under seismic event, the soils would be susceptible to liquefaction which could result in the proposed bridge being seriously damaged or destroyed. The Washington State Department of Transportation looked for several ground improvement techniques and found that blast densification was the most economical technique. Backup penetration tests showed a large increase in liquefaction resistance for the soil at this site. Then another case study, Westover Air Park North, Shikopi, MA. Blast densification was used to densify foundation soils for a large one-story manufacturing facility. Building was underlined by alluvial deposits. The alluvium consisted of saturated, very loose, fine to medium-grained sands with traces of silt and gravel. A seismic evaluation indicated the site would liquefy unless the alluvium was densified. Blast densification was selected over dynamic compaction and vibrocompaction as the best alternate. A blast densification test program was conducted at the site to verify the increase in soil density, determine the optimum blasting parameters, correlate density improvement with surface settlement, and to obtain ground vibration data. Electric cone penetration in situ test done before and after blasting showed that the soil strength was sufficiently increased to resist the designed earthquake at the site. Conclusion. Use of blasting methods in ground or soil improvement needs considerable expertise in the analysis, design, and implementation of the technique in the field. So that's all about the vacuum consolidation and blast densification. Thank you.